Hello everyone. Today we will start lecture 8, that is on remote sensing data analysis. So we will continue this course. You might have seen many images. When you capture the images using regular mobile phones or the camera, even then you will notice some of the images are not very clear. The brightness and contrast are not proper. Same thing happens with the satellite images also. So that's why raw remotely sensed images often have poor visible appearance due to poor brightness and contrast of the image, right? So that we will try to understand with this photograph. So here you see the first image which is taken, this is from IIT Guwahati. Now the second image, it is little bit better, this is again better, this is the last image, right. So here if you compare all of them together, then you will find this will have the poor brightness and contrast, and this is having a very good brightness and contrast. So this image quality, how they appear, how you see them, so that depends upon your brightness and contrast, right. So this you can observe here. So this is the first image, then second image, then third image, then this is the fourth image. And here you will easily notice that some of the features which are available here, let's focus on this cloud. Right. So when we have poor brightness and contrast, these things are not clear or these are not visible in our photograph. However, when we are improving the image quality in terms of brightness and contrast, we find that clouds are appearing here, right. So this contrast is very important. It is the difference in the intensity of the object of interest compared to the background. So if you draw a line, we are able to see this line because there is a contrast between the background and this line color, right. If I use white color, you will hardly notice, right, because both will have the same color. So there won't be any contrast. Contrast does not change linearly. So when I draw a line, the contrast is drastically changing here and on this particular line. That's why we are able to see the edges, right. It is a function of the log of the difference in the object and background intensity. That is obvious. This means that in the darker region, small changes in intensity can be noticed, but in the brighter region, the difference has to be much more. Let us take the example of night time. So very far, if there is a bulb glowing or a tube light glowing, that you will easily see that some light is there. But during the daytime, you will hardly notice if there is a bulb switched on or maybe a tube light outside. So it all depends what is the situation, how it appears, and what is the background condition. So the darker region, smaller changes in the intensity can be noticed. However, in the brighter region, the difference has to be much more. So in the daytime, you will hardly notice any bulb switched on outside, but in the night time, we all know, and even if it is half kilometer far and in between there is no object, you will be able to see some bulb is glowing or some light is there, right. So that is a very good example. Now referring to this statement, just try to see here. Now you see, when we are improving the contrast, what is happening? This cloud is clear in this photograph. So that means the remotely sensed images, doesn't matter whether it is a satellite based measurement or phone or your DSLR, the contrast or the brightness has to be adjusted, right. And this, remember, it is only for the visual appearance of the image. I am not talking about the analysis now. Analysis will come later. So there are different operators. So in the image, when we have set of DN values, and which is basically our pixel, right. So when we are having the pixels, So, this is let us say 10, this is 20, this is 30, something like that. So, when we have this image, we can have the local operation, point operation or global operation. So, we call it image operators, right. So, these image operators will help you to enhance the image quality. So, this particular portion is not explained here because this is the limitation of this particular course. So, here we do not have a scope of covering all the basic processing of this. However, all these details are available in my another NPTEL course, that is remote sensing and GIS. If you want, you can refer to those lectures. So, first one is the global operation. This do not consider location of the image pixel. So, this will be global, right. Then next is the local operation. So, here when the illumination condition is different across the image. So, suppose if this is 1 kilometer by 1 kilometer and part of the area was cloud covered. So, let us take this particular area was cloud covered. So, here this portion need more improvement, right. However, this other areas they do not need that much of treatment, right. So, in such cases local operation is good. If the entire area has the same illumination condition and the weather condition, then this global operation will be better option. Then the point operation, if you want to enhance a particular object or a target in that particular image, then point operations are preferred. So, this is the expression for point operation. You can see this is for the global, this is local operations are also considered, right, and then this is the point operator. So, when we talk about the image enhancement technique, there are many. So, majorly we classify them into two classes. One is the linear contrast stretching and another one is non-linear. So, when we refer to the linear, the image is enhanced linearly, right. And when we talk about the non-linear stretching, so here we have logarithmic stretch, exponential, piecewise, thresholding, density, and there are a few more image enhancement technique which comes under non-linear stretching. So, linear contrast stretching technique are not very useful in analyzing remotely sensed image. Why? Because when we talk about nature, in nature things are not changing linearly. So, classes are changing dynamically, right. So, the non-linear enhancement will be a better option instead of linear enhancement. So, that is why film, computer monitor, television and human visual system, these are the best examples of non-linear system. And when we are trying to represent our ground with the help of remote sensing sensors in form of images and then we use a display system to display our data, then non-linear image enhancement technique will give you better visual perception of that particular area. Non-linear stretch will become more effective to enhance the digital images. So, here this non-linear stretching we have example like logarithmic, exponential, piecewise, thresholding, density slicing, but we have one more which is called lookup table approach, right. So, here what happens when you use a particular image and just apply the logarithmic stretch, right. So, what will happen? You will have the output. So, once you get the output, you will not have any record of the previous data. This is the only output you will have, right. But when we talk about the lookup table, this lookup table will preserve the original image information. So, this will be also preserved. Whenever you want, you can go back from here to here, right. So, that is why it preserves the original image information, which is very important, because sometimes what happen, you have to refer to the original value for the analysis, right. So, let us talk about the histogram equalization. So, a dynamic gray range levels is preferred for better display. What does it mean? Suppose if this is the histogram and let us say this is 8-bit data. So, the range is 0 to 255. This is frequency. So, the histogram, let us say one case is this, right. So, here what is happening? All the values of my image is concentrated in this particular region. So, this particular region is not used by my data or the display system, right. So, here it may be 10 to maybe 50, let us say, right. So, even though I have the option of having 0 to 255 different classes or the gray labels, our data is occupying only 10 to 50, right. So, in such cases our image will have poor brightness and contrast So, when we are having this situation, can we use some method to enhance this data so that it should occupy this whole range, right. Then we can say this data is occupying the full range which is available to this, and then your image will be better, right. So, that is why a dynamic range of gray labels is preferred for image display. In the histogram equalization method, the image is transformed in such a way that all the gray labels have equal likelihood of the occurrence. So, what does it mean? When we refer to any image matrix, here basically let us say this is now we have 10, 10, 20, 20, 30, 5, 6, 9, 9, 9, 30, 20, 20, 10, 10. Now, here you see, if I draw the histogram of this, what will happen? I have unique value of 5, then 6, then 9, then 10, then 20, and then 30. This is not the actual scale. Now, if we identify the frequency, so this is 1, 2, 3. So, this may be 1, 2, 3. So, this is coming here. Now, for 6 we have 1, 2, 3. So, this is also coming here. 9 is 1, 2, 3. 9 is also coming here. 10 is 1, 2, 3, 4, 5, right. So, this is 5. So, 4, 5. So, 10 is here. 20 is 1, 2, 3, 4. So, this is here. Now, 30 is 1, 2. So, this is here, right. So, if you see, all these are having almost equal frequency because they are in the range, right. But suppose if I replace this value with, let us say, 7, right. Now, we have 7 here. 7 has only one frequency. So, in such cases what will happen? This value will not be seen in the image because other DN values have high frequency, means they are occurring more number of times. So, in such cases what happens? This histogram equalization method, this works on the DN values frequency and it tries to provide equal likelihood of occurrence to all the DN number present in my data, right. So, in such cases what will happen? Your image will be enhanced and this image will be better in brightness and contrast. Histogram based enhancement technique consider the relative frequency of the occurrence of gray label. Hope you have understood the previous example. High frequency gray labels should be given preferential treatment so that they should be well separated on the gray scale for better display quality. I will try to explain again this. Let us say 0 to 255 and this is the frequency. So, let us say my histogram is like this, but this available range we are trying to stretch this data so that it should be like this. It should be occupying the full display range, right. So, in such cases what will happen, this preferential treatment will be given so that the data sets will be well separated. So, one value is here, another value is here, but in this case, in this one, what will happen, this will be here, this will be here. So, these two will be well separated, right. So, that is the meaning of this statement. So, this histogram equalization is one of the best technique for image enhancement that you will see in the example that I will try to show. Optimizes the utilization of the available display range. So, the whole, in case of 8-bit data or 8-bit display system, the whole 0 to 255 gray range or gray labels will be used to display the data. It also merges the gray labels having very few pixels. So, suppose if the image is maybe 10,000 by 10,000 by 10,000 pixel, right. And here there is a few DN values, let us say 7, which is having only 5 frequency, right. So, there is frequency. So, in such cases this 7 is not a good idea to keep in this image. So, what it will do? It will merge it with the closest value which has higher frequency. So, let us say 8 is having 100 or 1000 frequency. So, these two will be merged. So, this 8 will have the 10,000 or 1005 frequency, right. So, like this it will be treating your data, and all these information will be preserved in the lookup table so that you can go back and refer to the original value, and it separates heavily populated gray labels that we have already discussed. So, an ideal histogram will have an equal population of all gray labels. So, I have one example. This is the input histogram and this is the output histogram after the histogram equalization, right. So, you can see how it is occupying this whole range. Let us say this is 8-bit data, this is 0 to 255. So, this range was not used, right, but here everything is used, right. So, this is what we are trying to do with histogram equalization. We will try to provide equal opportunity to all the pixels except a few pixels which is having very low frequency, that will be merged with the closest value, right. In this example, you can see this is a image matrix. So, image DN value, this is the image histogram, the input one. So, let us say 0 to 255, this is again 0 to 255. So, how do we do that? So, we use this equation to separate this heavily populated data concentrated in a particular range of this histogram, right. Now, we will be occupying this full range which is 0 to 255. So, here this is the round of the value whatever you will get from here. So, CDF is used. CDF is the cumulative distribution function, and this m into n is the size of the matrix. So, you take the total number of pixel in this and this direction you take. So, this is m by n, and L is your quantization level, that is 8-bit, 16-bit. So, in this case we have considered 0 to 255. So, this is 8-bit example, right. So, the same matrix has been used here in this table. So, what we will do, first we will try to identify the unique value, right. So, those are the DN values. So, 43 and so on, it is going up to 75. If you refer to this, the same table has been used here, right. Now, once you have this DN value, unique values identified here, listed over this table. Now, what we will do? We will go with DF, degree of freedom. So, what is this? So, 43 has occurred 2 times in this particular table or this matrix, right. So, here you have 2 times, then 44 has occurred 2 times. So, similarly, we will count it and then we will prepare this DF, right. In the next column, which is CDF, cumulative distribution function. So, here the first minimum value will have the CDF, which is 2, which will be equal to your degree of freedom, right. Using this image matrix, we will prepare a table, and this table will have DN values. So, here the first column will have the unique DN values from this particular matrix, and that will be listed over here. So, the minimum value, which is 43, and the maximum value, which is 75, that we have got from that particular matrix. Now, we will have the distribution function DF. So, the DF is basically the frequency, how many times 43 has occurred in this particular table, right. So, this distribution function will be listed here for all these unique values, right. And then we have this third column, which is CDF, cumulative distribution function. So, this 2, the first CDF of 43 will be same as your DF, right, distribution function. Now, what we will do? We will add this 2 with this 2, right, and then this will become the CDF of 44, and then same thing we are adding here, we are adding like this, and then we are getting the CDF of all these values. So, remember, this CDF is very important, because if you refer to this, here we will be using the CDF of a particular pixel, then we will be using the size of the matrix, then whether it is 8-bit or 16-bit data, and the CDF mean, which is here. So, here CDF mean is 2. So, same way we will be calculating it one by one for all the pixel value, and then we will have the equalized value, right. So, this equalized value will be based on this equation, and here the CDF mu, that is the for a particular pixel. So, in this case, let us say this is 2. So, this 2 value is used, then CDF mean is also 2, then m by n, that will be 144, because this is the sum of all pixels, how many times it had occurred. So, this is a very good idea to cross check whether this is matching with your m by n or not. And then you have again CDF mean, L is your quantization label. So, whether it is 256 or 16-bit or 18-bit, whatever radiometric resolution you want in your data, right. So, same way we will be able to produce the output image, and remember, this calculation will be preserved in this lookup table, and any time you can refer to the original value. So, whether this 119 had 43 value or 44 value, that you can refer any point of time. This is one example, and it explains the effectiveness of the histogram equalization method. So, just see this image. This is the raw image which is captured by a particular camera, and this is the histogram equalized image. So, you can see the difference, how well it is improving the brightness and contrast of the image. In this one, this is a satellite image. Here you can see how it has been enhanced. I hope the application or the effectiveness can be seen here with these examples. I have one more example. You can see how it is differentiating, or how well it is providing the equal opportunity to all the pixel value to appear in that particular histogram, right. I hope these examples have given you the explanation of histogram equalization method, how it is improving the image, and this can be implemented or it can be applied over any raw remotely sensed image or any camera image or any image that you have taken through your phone. So, with this I will end this part 1 of lecture 8, and we will continue this in part 2 of lecture 8. Thank you for listening.